The physical condition of the greenhouse air can also be expressed in terms of vapor pressure deficit, or the VPD. Indeed, it is the difference or the deficit between the amount of moisture in the air and how much moisture the air can hold when it is saturated. Or alternatively, it is the difference between the theoretical pressure exerted by water vapor held in saturated air and the pressure exerted by the water vapor that is actually held in the air and being measured at the same given temperature. To better understand the concept of VPD, have a look to this graph, which is expressing the vapor pressure deficit there's a difference between the water holding capacity, total water holding capacity of a certain greenhouse air, and this corresponds with the absolute humidity at 100% relative humidity with the current absolute humidity of the same air, of the same greenhouse air. In our case, you can see that the total water holding capacity of saturated air in 25 Celsius degree is 20 gram per cubic meter of air, and the current absolute humidity, which in the same temperature is practically 14 grams per cubic meter, and thus we have the vapor pressure deficit equals to 6 grams per cubic meter. As I said, alternatively it can be expressed in terms of vapor pressure, and in such cases it can be expressed either in millibars or in kilopascals. This is a graph expressing the vapor pressure deficit in kilopascals, and you see that it is split in different colors. Indeed, the optimum values of the vapor pressure deficit range from 0.9 to 1.1 or 1.2 kilopascals, and are expressed with a deep green color in this graph. And then gradually the values becomes smaller and smaller, which means the vapor pressure deficit is lower and lower, or becomes larger, and therefore the vapor pressure deficit is become also larger and probably too large. We will discuss about that respective values later on in this presentation, but you can find yourself this graph in the link which is shown to the end of the slide, and you can yourself try to find out what is the concrete vapor pressure deficit of your own greenhouse. Of course, this is a very valuable indicator of the physical conditions of your greenhouse air, and you can use it to identify the specific needs of your own crop regarding the water vapor in the air, or the needs for irrigation and similar things. Let's see in more details what's happened, whether the VPD values are either too small or too large. In case that the VPD values are too low for a relatively long time, specific problems will appear in the plant. Indeed, the plant will have thicker and larger leaves, they will have thick stems and longer internodes, but meantime the root system will be weak and shallow. But the most serious problem is the low transpiration rate, and this is followed by a lack of nutrient supply and the overheating of the plants. This is easily understandable because through the transpiration rate, the flow of water into the plant is regulated, and that means that some nutrients might be lacking under such a condition, and most often it happens in rainy days and with specific micronutrients like iron. And as well, most of the water transpired by the plant just to keep its temperature controlled. And in case of low transpiration rate, sometimes a specific physiological disorders is appearing. The boiled leaves at the top of the plant. In addition, you know that a low VPD means that the relative humidity of the air is too high, and this is a situation at which the fungal diseases can be easily spread off and might cause serious problems into the plants. On the contrary, in case of high VPD values for a relatively long period, the plants will have a totally different appearance. They have thinner and smaller leaves, they have thinner stems with higher content of dry matter overall in the stems and the leaves. They will have a stronger root system, and which is better developed and goes deeper into the soil. But the problem in such a cases is of course the high transpiration rate, and it might happen that because of the high transpiration rate, there will not be enough water entering into the plant through the root system to support the high transpiration rate of the plant. And because of that, the plants might have temporary wilting in the most hottest hours of the day. You can easily observe that in hot sunny days, that in the midday some temporary wilting is occurring in the plants, and they recover themselves after a few hours later when the temperatures are dropping down. Indeed, the optimum VPD values are different for different stages of plant growth. So, immediately after transplanting, you need to be aware that the young transplants experience a lot of stress because they have already lost a large portion of their root system, and they are still trying to form the new roots. And because of that, you have to target a higher humidity and VPD closer to the lower end of the general range we show in the previous graph. The ideal VPD in such a stage of plant growth is close to 0.8 kilopascals. During the vegetative stage, plants are indeed bigger and more robust. You can reduce the humidity in your environment in order to increase the VPD, and this will increase water and nutrient uptake, but however, anyway, don't increase the VPD too much. This will cause the stomata of plants to close, causing them to absorb less CO2. The ideal VPD for the vegetative stage is close to the middle of the general range and should be around 1 kilopascals. And finally, at the flowering stage, the plants are robust, but the flowers are sensitive to various issues, and you need to avoid excess humidity. The ideal VPD for the flower stage is closer to the top end of the range, and something like 1.2 to 1.5 kilopascal is the best one. As we said, you have to maintain a certain vapor pressure deficit in order to allow some transpiration from the plant. However, there are some specific cases when in purpose we keep the VPD close to zero, which means that we do not allow transpiration from the plant at all. And this is the case of the vegetative propagation. And this is mostly used in olive seedling propagation, when short cuttings are being placed in a substrate, in an artificial substrate, to root, and until the plants have no roots, we have to keep their leaves alive, not to let them wilt, and this can be managed by having the VPD close to zero. And another specific case is grafting. I'll talk about this in details in the next lesson. However, we could say that we have to keep the plant, the graft components and the sign practically non-wilted until some relationships are established between the rootstock and the scion, and then we'll gradually increase the VPD values until they reach their normal values. We'll talk about this in detail in the next lesson. To maintain optimum VPD values in the greenhouse, you need to correct the current VPD, and you can do that either by decreasing the current VPD values or to increase them. You have two different alternatives to decrease the current VPD values. First, to increase the actual vapor pressure, or otherwise to increase the content of water vapor in the air, to increase the absolute humidity. And you can do that by frequent irrigations, which intensifies the evaporation from the soil, greenhouse soil, or even better by misting, which delivers small droplets of water into the greenhouse air, which very quickly transform into water vapor and thus increase the absolute humidity of the air. And the second alternative is to decrease the saturation vapor pressure, or otherwise to reduce the water holding capacity of the air, and that can be done by reducing the air temperature of the greenhouse. You can do that by increasing the ventilation rate, or by shading, or other alternatives which can help reducing the air temperature of the greenhouse. In order to increase the current VPD values, you have also two alternatives: either to reduce the actual vapor pressure, which means to reduce the current absolute humidity of the air, and the best alternative to do that is to increase the ventilation rate, and thus you replace the humid air of the greenhouse with less humid air from the outside, and this contributes then to increased VPD. And the second alternative is to increase saturation vapor pressure, thus, or else to increase the water holding capacity of greenhouse. You can do that by increasing the greenhouse air temperature, and this is something being done in modern greenhouses, and especially during the nighttime. You can operate the heating system just to increase the temperature of the environment, to increase the temperature of the air, greenhouse air, not in order to not let it to reach the dew point, and thus you keep a certain limit of the VPD. However, this is an expensive method. You have to invest a lot in heating systems, and you have to spend money on running the heating system. So from this point, enhancing the ventilation seems to be a more realistic method for normal greenhouses in the Mediterranean region. As a conclusion, I could say that there are a number of factors which increase the water vapor presence in the greenhouse air, and also there are other factors which reduce the water vapor presence by releasing the water vapor outside the greenhouse. Clearly, these factors reach a certain balance, and this water vapor balance of greenhouse air can be expressed by this equation here, and you can find here all the explanation for all the factors which contribute in this water balance, starting from the rate of change of the internal humidity, the water vapor concentration, or else absolute humidity of the greenhouse air, the volume and the area of the greenhouse, the transpiration rate of the crop, very important, and the soil evaporation. Then follow with the water supply into the greenhouse from misting or the cooling pads, and on the other side there are losses from the water vapor from leakage and ventilation, and water losses from the condensation of water vapor on the ground or the vegetation. However, this is a long equation, and for practical reason we should shorten it by several assumptions, such as that during daytime the greenhouse water balance depends mainly on the evapotranspiration and on the loss from the ventilation. Condensation is seldom during the day, but however it should be considered during the nighttime. Next assumption is that the soil evaporation is generally negligible if localized drip irrigation is being used in a greenhouse, and at the end, in the majority of cases, no water supply from mist system is available in the common greenhouses. So, considering all these assumptions, this equation of the water balance can be shortened, and this new formula expresses in itself the level of air humidity in greenhouse as reference to the outside humidity and some other factors like the evapotranspiration rate, the crop transpiration, and the air renewal rate. Thus, now we can use this simplified formula for practical purposes. And for example, if we want to reduce the greenhouse humidity, these steps should be taken or could be taken to reduce the evapotranspiration rate, use shading screens or whitewashing in order to decrease crop transpiration rate in hot sunny days, and to increase the air renewal rate.